So anyway, yesterday we had started talking about the formula, and yes, sometimes it's really obvious to look at the values for enthalpy and entropy and sort of eyeball it and tell if it's going to be spontaneous or not. I just gave you another way to look at that. The bottom line is Gibbs free energy has to be negative in order to be thermodynamically favored. And you guys just read about exergonic or endergonic. If Gibbs free energy is negative, that's where we get the word exergonic from. That means that the system, the reaction in the system can perform work. And so that negative sign shows that work can be put out of the system. Just like exothermic means that heat can be released. But these words are not the same. Okay? You can have an exothermic reaction and it not be spontaneous and it not be able to do any work. Okay? So, anyway, these aren't, like I said, they aren't the same. If this is positive, then it's endergonic, right? And that means that work has to go into the system for the reaction to take place. These words will be very important when we get into next unit because we're going to be looking at batteries and electrochemistry and how to make electricity out of chemical processes. And so we'll come back, Gibbs free energy will kind of be our friend again. Then it's on the formula sheet. It's like, there's two that we haven't done yet, and it's like one of those. It's got like an F and an E and craziness. Did y'all see that one on there? You're like, what is that? Yeah, NFE, that guy. So we're coming back to this. So this is an important thing to go ahead and keep in your mind. This whole negative and positive and can it do work, that's the thing. So anyway, and we already talked about this. We got this. We can do this formula. Let's do this formula then. It'll be fine. So when we calculate Gibbs free energy, you can use that formula, or you can use the values in the back of the book and that formula on the formula sheet where you take the free energy of the products minus the free energy of the reactants. And you did some of those for homework, no big deal, right? So here, this is what you guys did for homework. So why don't you give this one a try? Is this one not? Is it already worked out on your paper? No, do it then. Oh. What happened? Yeah, your homework that I just gave back to you that you turned in yesterday. So go ahead and use the Gibbs free energy is equal to enthalpy and minus temperature and entropy. And make sure that you are paying attention to your joules and kilojoules. I don't know why. I mean, I do know why, but it's very annoying that they're not the same. I'll be doing it up here, and you can look up here if you want. I have it worked out on a piece of paper somewhere, but of course I don't have that. So let me know if I mess up. I'm sure you will. Don't be scared of me. It's scary. Hey, maybe I'm scary. Let's figure out which one comes first. Oh, yeah. I hear the calculators breaking out. I like it. Yes?
When you convert to Kelvin, Kelvin is adding 273 or 278?
270. Am I? Oh. Just kidding. You know why I did that? Let me tell you why I did that. This is a good discussion. Because room temperature is 298. That's why I did that. My bad. No, you're totally right. Thank you. Just kidding. I don't know.
Is free energy always in that kilojoules? Or it can be either?
No, yeah, kilojoules for that one and for enthalpy, but then entropy is always joules. And so, so I guess I'm off by 5. My bad. Thank you, Megan.
I was lost whenever I did that one.
So, do you want me to start from the beginning on this? Sure, absolutely. All right. So, if you don't know how to do these, on the formula sheet to calculate Gibbs free energy, you're gonna, if you're given the equilibrium constant like a capital K, you're gonna go for the, are you looking on your formula sheet? You're gonna go for the negative RT natural log of K. Do I have anything up here about an equilibrium constant at all? No. So we're gonna actually, that's like the next lesson after this one. So I have been given temperature, I have been given entropy, and I have been given enthalpy. And so that's all the variables I need for that top formula. And so all I'm doing right here is I have to fill stuff in. The trick is I have to always make sure that I'm working in kilojoules and then I'm working in Kelvin. So if I'm going to convert that to, so this is going right here, this is going right here, and this is going right here. And so that's fine. I can go ahead and plug that in. My temperature is going to be 273 plus the degrees Celsius. So 305 is my temperature. And then the entropy, I'm going to need to convert that to kilojoules. And so, la la la. Basically, you're dividing by 1,000, whatever. So what you're going to do now is you're going to be filling this in to that. You're going to be filling this temperature into that. And you're going to be filling this enthalpy into that. And you just solve for Gibbs free energy. So why don't I give you guys a second to put that stuff in there and make sure you know where to put it. The answer, I don't know. I'll show you the answer. I'll make that thing do the thing, and it'll tell us the answer. Can I erase this? Is that okay? The work will come right back. It'll just be prettier. Oh, just kidding. Oh, do you know how that, like last time I did this, it like randomly went back to slide 11 or whatever? All right, and so like I said, you just fill this information in. There's where they added the 273, and then here's where they divided to get the joules to kilojoules. And then the value there is 15.3 kilojoules for the Gibbs free energy here. And so since it's positive, it's not going to be thermodynamically favorable. How you doing? So you just kind of rearrange on some of them. You have to rearrange, but it's not bad. I think this next one, this one's already on your paper, isn't it? One of these is, yeah. And so if they ask you for temperature, I think you'll, after having this class for 4 months, you can probably rearrange this formula for temperature. Would you like me to show you that? I'll do it. Okay, I'll do it. When you have a lot of variables and units and stuff, it is easier to rearrange it first, or at least I think it is. This second one, I keep doing that. It'll just have to be like, what is that, Osiris's eye on top of the pyramid?
Yeah.
Sisu. That looks really bad, but it's a pyramid. It's a thing on a dollar bill, you know. So if I'm solving for temperature, because it's getting multiplied here, then I'm going to need to, let me just back up and plan. The question said, Let me explain why I'm doing this. What temperature does this have to be to become thermodynamically favored? And so to be thermodynamically favored, if I set Gibbs free energy to 0, any temperature above what I solve for, it will be thermodynamically favorable. So that's a good starting point. So if you set it to 0, then you can kind of work from there. So anyway, if you make Gibbs free energy 0, and since this is getting, I'm solving for temperature, right? Since this is getting multiplied, I'm going to go ahead and subtract my enthalpy value over here. It's a really long minus sign, just in case you can't see it in the back. I'm just kidding. So now I can divide both signs by my entropy. And then I have a negative delta H. These triangles are tripping me out today. And then this side is also negative. And so it's actually, I didn't mess that one up. And then, so on the PowerPoint slide, you can see how they got this. But I just want to show you the steps there. Okay, and so again, you're just going to be filling stuff in. But if it ever asks you a minimum entropy or a minimum temperature or whatever, set Gibbs free energy to 0, and then you know that's the minimum it could be. So that's what they did. There's a lot of you'll have a lot of practice on this, so I feel like if I move along, you'll get to practice more, and I can totally help you then. Here's that chart, though. That just looks awful. I don't like it. I don't like the chart. Draw your little happy face men, or do whatever you want. I'm gonna draw my happy face men until I die. So anyway, we can draw the happy face men. Sometimes you can kind of reason through it. No, but look, yeah. You want to draw the happy face men so you can figure it out? I mean, you don't even need to draw it because entropy increases and it's exothermic, always favorable. But if you needed to, which we totally can, because you're going to get on the AP exam and you're going to be like freaking out. Oh, not even the AP exam, your final exam, that thing. Yeah, that one. So we always have to start with S. Don't forget. So delta S, and it's positive, so it's greater than 0. And then my delta H is negative, so it's less than 0. I'm in love. So it's totally spontaneous. So there you go. This is the cutest thing.
I can just imagine on AP exam they justify your answer for like 15
Well, if you justify your answer, the justification is that enthalpy is positive. Excuse me, entropy is enthalpy is negative and entropy is positive. So it's exothermic and the entropy increases. So
They were like, yeah.
whatever. And so, like I said, you guys, you can. This thing, I feel like we've rode this horse before. We've been here. We visited this place. We've taken pictures, and you're gonna do some more of these. You used the thing in the back of the book. Don't forget your stoichiometric coefficients. So there's a 2 and a 2, and you feel these. I hate these. Look at me in the face. Are you looking at me in the face?
Yes.
I have never seen any question with this form, even though they gave you all 3 on here. I've never, ever, ever seen this on any kind of question of any test. So, we're going to do some, but that chart thing is the problem. So, anyway, I already said this yesterday. I made a point of saying this. Thermodynamically favored processes are not always fast. So like I said, rusting can take hundreds of years. That's the reason they changed it from spontaneous to thermodynamically favored, because it takes so freaking slow to say it. I guess they're trying to get across to you that it doesn't have to be fast. I hate that. This is like way too much. So anyway, this is the coupling thing. Yeah. So go ahead and cook on numbers. All right, so the chart a couple slides back this little guy right here, let me go back a couple slides. This is no fun, and this is hard to remember. So what I did to help you guys do your homework is I kind of made up a story. So as you look at this, I'm not talking to y'all, I'm talking to the computer. Yes, Amelia and Avery, I'm talking to you. Anyway, as you look at this, this is really confusing, and so on release exam questions, there's a lot of times where they'll give you entropy and enthalpy values, and they'll have negative and positive values, and you'll have to say if it's thermodynamically favorable or not. So anyway, if we start with what is always thermodynamically favorable, and by the way, you have to start with S because starts with S. Go ahead and put your entropy up. And if it's always thermodynamically favorable, entropy will always increase, so it's going to be positive. So it's greater than 0. And then the enthalpy will always be negative. Exothermic reactions take the system to its lowest energy state, so less than 0. And so when I was looking at this last night, I kind of saw these little eyes and noses, and I saw the mouth. See it? Right there? Whee! And so when things are spontaneous, like, I don't know, love at first sight, also thermodynamically favorable, you can see that they kind of stare longingly in each other's eyes. And this little relationship here will be thermodynamically favorable. If we kind of take this and reverse it to what is never thermodynamically favorable, the entropy is going to decrease, so it's going to be less than 0. The enthalpy is going to have a positive value. It's going to be endothermic, so it's more than 0. And if I draw my little eyes here, my little mouth and nose, they're definitely not in love. And so this is never spontaneous, thermodynamically favorable. Okay, and so for the other two that are in those other boxes that you can never keep straight, yeah, those, if we draw those in, and they're going to be kind of facing the same way. They're both going to be negative, or they're both going to be positive. You can kind of draw their little mouths in. Like this guy's interested, this guy's looking away, girl, guy, whatever, it doesn't matter. Everybody's special and loved, it's fine. So with this, this is only thermodynamically favored. Look at, I think about this enthalpy as heat. When I have a small heat value, see, that means that this is going to be thermodynamically favored only at low temperatures. And if I face them the other way, well, the sky is positive and the enthalpy is also positive. Now I can see my heat, it's enthalpy, but the heat is high, so this is only going to be thermodynamically favored at high temperatures. So this energy, oh yeah, so when you have Gibbs free energy as positive and this is endergonic, that means work has to go into the system. So what's going to end up happening is it's going to be paired with a reaction that is exergonic, that can do work to this system. And so that's what we were talking about with like respiration being paired with the formation of ATP, ATP from ADP, with ATP being more complex. Electricity can be used to recharge a battery. Photons can supply the energy required to move electrons. And like this is what I was saying, making glucose, you can see the Gibbs free energy on that is very positive, but it's started with the absorption of photons, and so you have this outside energy source, the sun, that is fueling it. And so there's this whole like electron chain. It's really cool. When you get to AP Biology next semester, if you're doing that, they'll talk about how the electrons actually go through this process of making glucose, and it's really interesting. But there's obviously, if we don't have the sun, can't do photosynthesis, but the reason for that is because it gets free energy of this process of making something very complex, is positive. So that's why the sun burns out. We all die. So, if we break down some glucose, there you go, ATP to ADP. Notice if you go the other way, the gives free energy is positive, right? So we put those together. We can couple these together. Oh, this one's positive. What is this one? Metabolic break. Oh, well, anyway. This crazy thing is positive. This one's negative, but it's cool because it works out in the end being negative because they're coupled together. I don't know. Doesn't matter. Okay, so that's how that works. If something is endergonic, but it actually gets carried out, it's going to be coupled with a process that's exergonic. That has a negative gives free energy. That makes good sense, right? No big deal. All right, so you have the whole rest of the time to do your